All right, so the first thing you have to know how to do is how to find sine, cosine, tangent, cosecant, secant of various stuff. So sine, and I'll give you a blank unit circle, but you don't have to fill it out. You can just use it to sort of like reference things. So is 13 pi quarters something that's on your unit circle even if I'd given it to you? No. So what is the biggest quarter pi you have on your unit circle? I think it's 7 pi over 4. Because you can think about 2 pi is the same thing as 8 pi over 4, right? So the biggest one that you have is 7 pi over 4. So you got to keep, does that make sense? Over 4, yeah. So keep counting around until you get to 11. So there's 8 pi quarters, 9 pi quarters, 10 pi quarters, 11 pi quarters, 12 pi quarters, 13 pi quarters is right there. Does that make sense? Okay. So at that angle, what is the sine? Negative root, I just couldn't hear you.
2 over 2.
2 over 2, yep. The cosine would be the same thing, right?
I find it easier to subtract pi over 4. I mean, 8 pi over 4.
Yeah, that works too. You could do 13 pi over 4 minus 8 pi over 4, and that gives you 5 pi over 4, right? That you take away the whole rotation and figure out how much past the full rotation you've gone. That's also totally fine. Okay, secant of pi over 2. So secant is 1 over which function? 1 over cosine. And at pi over 2, what is cosine? 0. Can we do 1 over 0? No. So this is undefined. Morning. I have a paper to give you. Pass them back. Okay. Awesome. So if you get something like that, just make sure you say it's undefined. I'll be expecting you to be able to recognize that. Okay, tangent of 7 pi 6. So in your little circle, 7 pi over 6 is 1 pi 6th past pi, right? Okay, so that's right here. So what are the coordinates of that little point there?
Minus root 3 over 2 minus 1/2.
Yay. Okay. And tangent is equal to sine over cosine, right? So at that angle, what is the sine? I think that might be the cosine. The sine, yeah. Negative 1/2, yep. And the cosine is negative root 3 over 2. So that would be 1 over root 3, right? Which if you rationalize the denominator by multiplying by root 3 over root 3, what does that give you?
3 over root 3. I mean root 3.
You mean root 3 over 3. Yep, I understand.
Do you want it?
I would ask you to do so if I did, but I know that Alex definitely wanted you to do that. Does that make sense? So like if you were, say, doing like your Alex assessment, make sure you rationalize the denominators. I'd have to ask for it. Okay. Even and odd. I think if you were here yesterday, you reviewed what even and odd means, right? So if a function is even, what happens when you plug in negative x?
You get the same as we can just plug in regular x.
Yep. And if it's odd, you plug in negative x, you get the original function multiplied by negative 1. So everything will be the opposite sign. That's not quite true, but okay. So first one, so let's plug in negative x. You got cosine of negative x plus 7 times negative x plus 5. So what kind of function is cosine?
Even.
Even, so that is just cosine of x minus 7x plus 5. Okay, so is that the original function?
No.
No. So is it even?
No.
No. Is it opposite the original function?
No.
No. So that makes it neither.
Still got their classes of neither.
Neither is, no, not that I know of. Neither, you're either even, odd, or neither. Those would be like three distinct sets that together make all functions. You okay with that? How about this one? So what kind of function was sine?
Odd.
Odd. Negative x to the fifth. Okay. So if sine's odd, the negative can come out of it. If you do negative x to the fifth multiplied by itself 5 times, is the resulting thing negative or positive? Negative. So what happens when you got a negative over a negative? So they cancel, and that's the original function again, isn't it? So that means this function is even. So because this is still new to you, I want to see that you know how to plug in negative x and the result that you get. Like, that's what I want to see for work. Once you get faster at this, like if you take calculus, you can kind of just like look at the function and tell by plugging negative x in your head. Does that make sense? Okay. What if that denominator would have been x squared? What would have happened then? It would have been odd, because if the denominator was x squared, that would have made this a positive x squared, right? And only one negative sign would have been the whole thing just being a negative expression. Okay, are you okay with even odd?
Yes.
Yes, Tiny, let me know you're done writing, okay? Good? Okay. All right, so find the period and amplitude, if it's applicable, of the following functions. So I think you reviewed yesterday, what is the base period for sine, cosine, cosecant, and secant? What is the period of just a regular one of those functions? 2 pi. Tangent and cotangent, what's the base period for those functions? Pi. And one reason you can think that cosecant and secant are the same as sine and cosine is they're either 1 over cosine or 1 over sine, right? Okay. So to find the period, you say, when does x over 4 equal 2 pi? When that happens, that's the x that will be the last part of the cycle, the very last point. So what x makes this happen? 8 pi. And does that oscillate slower or faster than a regular cosine function?
Slower.
It's slower. That's mostly just for reference in case you had to graph it, like relative to regular sine function, it's going to have like a longer wave. Does this function have an amplitude? Yes, its amplitude is 2. Only sine and cosine have amplitudes. That kind of refers to, it's twice the height. Does that make sense? It's the deviation from the center. Tangent does not have an amplitude, does it? Because tangent's picture, it goes like in like an S shape and it's infinite in both directions, right? It doesn't really have a height in some sense. So how would you find the period of this function? So that 2x equal to pi. And so x would be pi halves. Is that narrower? Like, is it? Yes. Yeah, it's going to be narrower than a regular tangent function. Does that make sense? Say that again, Tani?
Would it be faster because it's narrower?
It'd be faster, yep. You could think about it also as being a faster kind of thing, is that it goes through its cycle more quickly. All right, how about secant? What would you set 4x equal to? 2 pi in this case. And so x would equal 2 pi over 4 or pi over 2. And would that go faster or slower than normal secant?
Faster.
That'd go faster. I think that the best way to think about that is to think about that x as being time. And if you take time multiplied by 4, stuff goes faster. If you take time divided by 4, stuff goes slower. Does that make sense? That might be a good reference point for should this oscillate more quickly or less quickly than a regular sine or cosine curve. Okay. A big part of this will be, can you graph some functions? And I know graphing is the thing that gives you the most trouble, so I think the first thing that you should do with this kind of stuff is figure out what the period and the amplitude are. So what is the amplitude for this function?
2.
2. Okay, and for the period, you set x over 2 equal to 2 pi. So x would equal 4 pi. Okay, and I said your interval was negative 2 pi to 2 pi. That means this is 2 pi. This is negative 2 pi. Here's pi. Here's negative pi. Let's start by just sketching in regular cosines. We kind of get a feel for what that picture looks like. Does that make sense? So where does regular cosine hit the y-axis? 1, right? Regular cosine hits the y-axis at 1. And then at pi halves it crosses, right? At pi it's down at negative 1. 3 pi over 2 it crosses. 2 pi it's back at 1. So there's just regular cosine. So what is this? The fact that the period is 4 pi means that curve is going to stretch out. Does that make sense? It's going to slow down. So this point, oh, that's at 1. Where's it going to be? So it's going to put it at 2. What part of the equation made that happen? Was it the 2 in front of the thing, or was it the x over 2? That 2 in front is what made it go up to 2, right? Okay. Now, if I had this thing graphed all the way over to, say, there's 2 pi, let's call this 3 pi, let's call that, you don't have to graph it to 4 pi, but let's just do it to show you what would happen. So, when would this graph cross the x-axis next? Pi. You see how that's 2, this was pi over 2, that times 2 makes pi. This point right here that was at pi is going to now be at 2 pi instead, right? It'd cross at 3 pi, and by 4 pi it'd go back up. The only part you have to, oops, and I made a boo-boo. This point should be, where should that point be down at? Negative 2. I didn't put it down far enough. So you only had to graph that part of it, but the rest of it would have looked like this. Does that make sense? Okay. And each distinct cycle of a cosine or sine curve kind of has those 5 major points in it. Does that also make sense? Okay, so if you had a crossing point at pi, where would another one be? In a negative direction. Negative pi. So it'll do this kind of thing. And then at negative 2 pi, where's it going to be? Negative 2. Say that again, Tawny?
2 at the front of the problem made it wider.
The 2 at the front of the problem made it taller. I think that's what you meant to say, right?
Yeah.
And the x over 2, that's the part that made it wider. Yep. If you were uncertain, you could also plug numbers in. Does that make sense? Like you could plug numbers in the equation. Like if you plug in pi, you'd get cosine of pi over 2, which is 0. So, but that's what this picture will look like. Oh, man. Okay. 1/2 sine of x minus pi over 4. So, this is the graph of y equals 1/2 sine of x shifted how? To the right, pi over 4. What if I added a number outside the sign? What would happen to it then?
It would go up. Maybe shift it up.
Up or down, doesn't matter if it's positive or negative number, right? Yep. Okay. So let's start by just graphing regular 1/2 sine x. And because I gave you 2 tick marks and they're unlabeled, why don't we call this one 1, which makes that one 1/2? Is that all right? If you don't label them, I'm assuming you're counting by ones. Is that okay? If they're not by ones, you have to label them. So these ones always have to be labeled. Okay. So where would 1/2 sine of x start? We're 0, 0. And by pi over 2, where's it go?
1/2.
Up to 1/2. By pi, you're down at 0 again. By 3 pi over 2, you're at minus 1/2. And by 2 pi, you're back at 0. Okay, and there's the pattern in the negative direction. Okay. So now is pi quarters a reasonably easy bit to shift it? Because it's just half of a half, right? So shift everything right pi quarters. And I'll try to remember tomorrow, and technically speaking, like on this left side, your picture would also, if I said negative 2 pi to 2 pi, you'd have to kind of like draw it going down a little bit there, but I'm not gonna be super picky about that. It is really easier to sketch the parent and then talk about shifting the points there. I'll bring in a bunch of colored pens for your test tomorrow, so you can like have different colors to draw with if you wanna draw like a parent in one color and a translated function in another color, okay?
Do we have to do that?
You don't have to do that if you don't want to. It's only if it'll make if it makes your life or my life easier. If you can draw one like really lightly and then the final one really dark, that's also totally fine. Or one dashed, yeah. Either way, some way to distinguish what's the parent and what's the actual answer.
Do we like have to draw the parent?
If you can get away without drawing the parent, you're fine, okay?
Despise doing that.
I
That's
understand.
me for some reason. Like it breaks my brain.
I think it just, for me, the more complicated it is, I have to actually think about, okay, move this point over, this point over, this point over. But, you know, everyone thinks differently. As long as you do it right, I'm not going to diss you. Okay. Holy moly. Okay, how about 5 tangent of x over 2? So I think the first thing we should do is figure out what the period is. Does that make sense? So what do we set x over 2 equal to? Pi. So that means x equals 2 pi. Okay, so here's 2 pi, here's negative 2 pi, here's negative pi, there's positive pi. So I'm going to sketch this in just very briefly. You don't have to. Where are tangents asymptotes normally?
Every pi or
Negative pi over 2. That would be regular tangents, right? And at positive pi over 2. And the width of that is pi, right? So when you effectively double that, where does it throw the asymptotes?
Negative pi.
Negative pi and pi. And you see how the width from end to end there is still 2 pi, right? Does that make sense? So I'm going to erase the ones that are the base tangents asymptotes, but there you go.
Oh, morning.
So are there going to be any more asymptotes that are part of the graph that we're looking at? No, because where would the next one actually be? It'd be at 3 pi, wouldn't it? Because it'd be 2 pi past pi. So there would be one at 3 pi, and let's just sketch that there, only you don't actually have to have it, but just so we know that's where the next ones are.
But why would it be that far?
Because the total distance from asymptote to asymptote is 2 pi. So to get the next one, you add 2 pi to pi. So pi plus 2 pi is 3 pi.
Oh, okay.
Think about it as a stamp. Like you have this middle thing in the middle that you're going to take and you're going to stamp it repeatedly to get the rest of the picture. And so your stamp's width doesn't change.
So when we were smaller, and we went to bigger, we put half of it on one side and the other.
That's because it's tangent, yeah.
Oh,
If it were cotangent, then it wouldn't be half on either side of the y-axis because of what tangent's picture looks like, just for the regular function. Okay, and usually with tangent, when you plugged in pi over 4, you got 1, right? But now when you plug in pi over 2, you're going to get 1, except there's that 5 there, so guess how we're going to fix that? That's now 5. And so you go through this point, and this point, and what is tangent of 0? 0, so it goes through the origin, and then it has this sort of like S-shaped thing going on.
Did you just label the first ticklet pi halves? Oh, I can't remember.
It is pi halves, isn't it?
Yeah.
Yep, okay. All right, and then up until 2 pi, what? You see how this point is at 0, right? If you shift it over 2 pi, that puts this point also at 0, right? And will you have the negative half on the left of that dot or the positive half? Do you know what I mean by that? Will you be graphing this part, or will you be graphing this part?
The negative half.
The negative part, yep. So it looks kind of like ish. And then this looks kind of like ish. And you're only asked to graph from negative 2 pi to 2 pi, so that's good enough. If you graph extra, I'm not going to be like frustrated, but it would look like this. The most important thing with tangent is that you get sort of the direction correct and that you get the asymptotes in the right place. Does that make sense? What would putting a negative in front of that tangent have changed?
The
What would it flip the graph over?
X.
The x-axis. So you see how these pieces are all increasing, right? It would have flipped them, and so this part that's negative would be positive, right? This part that's positive would go down and be negative. So change it so each little piece was increasing. Think chutes and ladders, right? You've got ladders, right? If I had to put a negative, you have chutes. Did you guys play chutes and ladders? Yes? Okay, wait, what was your childhood like? Come on. Okay. Oh, secant of 2x. Woo. All right, so for this, I am going to start by graphing cosine of 2x. Because that gives me a really easy way to figure out where my asymptotes are supposed to be for my secant function. So for that cosine function, you set 2x equal to 2 pi. So x is equal to pi. What did I just find there? The period. I found out the period of the cosine function. So there's pi, there's 2 pi. Will this cosine function oscillate faster or slower than a regular cosine function? Faster. Great. And it will complete one full cycle in pi. Okay, so where does cosine start? 1, okay. Is it going to cross at pi over 2 or someplace else? If we're graphing cosine of 2x, that is, because that wasn't completely clear. It has to be done by pi, right? So that means by pi, it's also back at 1. At pi halves, it's at -1, so what are the points where it crosses? The quarters, right? Pi quarters and 3 pi quarters. But how you can start is you can say if I've gone through one cycle, I must start and end at the same number. Does that make sense? Okay, so what should you be at 2 pi? You're going to be back to 1. By 3 pi over 2, you're at -1, and you cross at 5 pi quarters and 7 pi quarters. Okay. So if you hate graphing parent functions, Jessica, does this one make you even more frustrated because this is sort of a weird sort of parent, it's not really even a parent function. They call it
It's just like, I keep looking up to check what I did.
Yeah.
And there's something else on the board, and I'm like, no, and then it's fine.
Okay, as long as it's eventually fine. Does my cosine picture look right?
I didn't do that.
Okay, so we'll see if you're, okay, I see, I understand. You did the rest of it. Now, where is this secant function gonna have an asymptote? At the zeros, and the zeros are where this cosine picture crosses the x-axis, right? So everywhere you cross an x-axis, put in an asymptote. Can you say chugga 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 when you do it? It makes it more fun. Sorry.
Wait, so why is that asymptote?
You tell me, think about it. What is the y value at all of those points? Uh-huh, and what happens when you divide by 0? You get a vertical asymptote. Because at these points, the cosine is 0, right? You're graphing secant, which is 1 over cosine. And when you have a 0, when you have got a number over 0 in the denominator, that makes a vertical asymptote. There's a lot of asymptotes for this little picture, aren't there? Holy moly. Is it looking better, Jessica? Like, as in, like, closer to yours? You got the asymptotes in the right place?
I'm just trying not to worry about that.
Until you get to the end. Okay, all right. And now everywhere the portions of your graph are above the x-axis, you're going to have these parabola-shaped bits above, like this. Below, they live down there.
You're not gonna have something just draw heavy, are you? On the-
Oh, I mean, maybe. It would have made it a little bit easier if I just asked you to graph like secant of x over 2, right?
Yeah, or you could just give the interval like negative.
I could give it to you negative pi to pi. That would also be fine, but it's not that bad. It's a little bad.
Wait, so why do we draw these only?
Because of the interval.
Wait, why do we draw these only, or why are there those purple things there at all?
Second one.
Second one, okay. So let's just look at this part only, okay? Just that part. So this number right here is 1, right? That's the value of the cosine function. What you do is, to find secant, is you do 1 divided by whatever number this is. So 1 divided by 1 makes 1, right? And as you go this way, those numbers get closer and closer to 0. Does that make sense? So if you do 1 divided by like 0.7, you get, so that's 1, well, so 1 divided by 0.5 is 2. Does that make sense? If you do 1 divided by a really, really, really small number, like 1 divided by a millionth, that makes a million, which is why these get bigger and bigger and bigger and bigger. And the same thing on this side. And the reason that these are down here is because it's 1 divided by a bunch of really small negative numbers. Does that make sense?
Yeah.
Okay. And drawing the cosine curve in the beginning sort of lets you determine, is my little portion above or below the x-axis? You know how I could also make it easier in your tests is I could have you graph cosine of 2x in one problem and then do secant in the next problem. So you'd already have it kind of there. Does that make sense? That'd make stuff easier.
So the answer would be the purple ones.
Yep, the black one is just really the work to get the purple ones. The textbook called the black one the guide function, and the purple one officially is the answer. Yep. Okay, you good? Alrighty. So find the exact values without using a calculator. If the expression is undefined, tell me this. So these inverse trig functions are tricky because you have to restrict your functions to a special domain so that they're going to invert. So what did we have to restrict sine x to? Do you remember what we restricted it to? Yep, negative pi over 2 to pi over 2. Tangent had the same restriction, right? What was the restriction for cosine? 0 to pi. And that was because if you didn't restrict it, they were not one-to-one functions and you could not invert them, so you had to look at just a portion of them. So finding tan inverse of negative root 3 is like saying tangent of what number gives me negative root 3 specifically in the interval from negative pi over 2 to pi over 2. So it's saying what angle gave me this value in that interval. So you're looking at just this part of the unit circle. And are you looking at this half of it? No, because in that half of it, the tangent is positive, right? Okay, so that point or that point. The first point's coordinates are positive root 3 over 2 1/2. The second point's, negative 1/2. The second point's coordinates are positive 1/2, negative root 3 over 2. What is that first angle? Pi over, negative pi over 6 officially, but my bad. The next one is negative pi over 3, right? And tangent takes sine divided by cosine, or y divided by x. Which y divided by x is going to give you negative root 3?
Second one.
The second one. So this will equal negative pi thirds. And notice how you only have one answer. One input, one output. Yeah,
Does it have to be negative pi thirds?
it does. Yeah, that is the tricky thing. That's what he's saying this would be in this interval means. It has to be negative pi thirds. So saying, what would that be? Saying 5 pi thirds, while is technically close-ish, is not quite correct because that wasn't part of the thing you restricted the tangent to. So I give you partial credit for kind of knowing what question you had to answer, but you do have to know that it has to be within this interval. Yep. And that's the other reason is that that's what we restricted the inputs of sine and tangent to. So when you flip-flop to get the inverse, that becomes, so this was the domain of the original function, which means the range is negative pi over 2 to pi over 2. Does that make sense? So the outputs must be spat out in that range of values. Yeah.
So why exactly did we choose these specific intervals?
Because if you don't, the part of the tangent function you're looking at is broken.
Okay, but where did those come from?
Where did this come from?
Yeah.
Okay, because if you look at regular tangent, this is pi halves and this is negative pi halves. And so when you look at inverting it, you want to look at one continuous chunk. And so that's kind of what's considered the main continuous chunk.
And that's why it's different from cosine?
Exactly. Yep, exactly. That's exactly why it's different for cosine. Yep. And that is the trickiest part about inverse trig function. Once you get the domains are restricted so you could look at one sort of continuous chunk of sine or cosine, then it's all fine. Okay, sine of what number gives you negative root 2 over 2? Negative pi over 4. And I can also give you a quick explanation as to why they chose those values for sine. So sine's picture looks like, so if there's pi, here's pi over 2, negative pi. Looks like that, right? And the part that gives you all the possible y values in one continuous chunk is there. That's why they chose that part. Otherwise, you'd have to take two broken chunks or take a chunk like from pi halves up to 3 pi halves, and that'd be just kind of weird. They just choose the one that was sort of centered around 0. Okay, now another funky thing is that inverse trig functions don't always cancel. And inverse trig functions won't cancel if you're not in the right sort of set of numbers there. So is this is negative pi thirds within 0 and pi? Crap. So what you have to do then is figure out what is cosine of negative pi thirds. Just work it out from the inside out. So cosine of negative pi thirds, I think, is 1/2. Is that correct? So that becomes cosine inverse of 1/2. And cosine inverse of 1/2. You ask yourself, cosine of what angle gave me 1/2 in the interval from 0 to pi? So is it pi 6? Or is it pi thirds? Pi thirds. And I would say if you're uncertain whether the sine or cosine cancel, this actually always works. Does that make sense? Like just work out what this first thing is on the inside and then do cosine inverse of whatever you get. And if by chance they happen to cancel, then you just got lucky, right? but you won't be wrong if you do it that way.
Would you get us less points if we didn't know right off the bat?
No, because I think then maybe you'll eventually get the pattern. Does that make sense? Yeah. Okay. So there is one more. And I think that this will be on your test. I like totally promise because it's something you have to know for calc. But did Erica go over these with you yesterday? I asked her to. So I can't remember if we did them in class or not. I think we did, but I don't know if I put them on a quiz. So it turns out weird stuff like this actually simplifies. And it simplifies to things that don't have any trig functions in them at all. And it's kind of crazy. So we're going to simplify sine of tan inverse of 2x. So this thing is an angle. You input a value of tangent and out comes the angle. So you let theta equal inverse tangent of 2x. Does it make sense? This is the same thing as saying tangent of theta equals 2x. Okay, and you can just assume that 2x is in the appropriate place so that the tangent inverse and tangent will cancel. And from there you use a triangle. And you can draw the triangle however you want. I just choose to draw it this way and put the theta in the lower left, but you could draw it the other way and put theta in the lower right. And you think about back when you first learned sine, cosine, tangent, what was tangent's definition in terms of a triangle? Opposite over adjacent. And it's not immediately obvious how that's helpful, but 2x is the same thing as 2x over 1, isn't it? So that means that the side opposite that angle is 2x. The side adjacent to that angle is 1. And this is a right triangle, so you can use your very, very favorite theorem to find the other side. Does that make sense? So call that side C. It'd be 2x, the whole thing squared, plus 1 squared equals c squared. So what is 2x times 2x? 4x squared plus 1 equals c squared. So c equals the square root of 4x squared plus 1. I don't need a negative, yes?
I did this with x and 1/2. Is that going to be wrong?
No, I don't think it will. You made that into x over 1/2.
Mm-hmm.
Your answer will look a little bit different, but it should be equivalent. Yep. Is everyone okay with why that's only positive? Because it's the length of a triangle, so it has to be positive? Okay. And then here's how you find the sine. You say this is equal to, your original problem is now sine of theta. Why is that okay? Because theta is equal to tan inverse of 2x, right? And then you use the tan inverse of 2x to make this triangle, right? So go back to the triangle and find sine of the angle from the triangle. So sine is, so opposite over hypotenuse, right? So which side is the opposite side? 2x. What is the hypotenuse side? So yours, Jessica, might look a little bit different, but I think it's equivalent. Did you get this, or does it have like an over 2 and stuff in it?
X divided by the square root of 0.5 squared plus x squared.
0.5 squared plus x squared. So here's how it's the same. That's the same thing as x over the square root of 1/4 plus x squared. Does that make sense? And then if you multiply this by 4 inside the square root, that gives you the 4x squared plus 1. And multiplying by 4 inside the square root is multiplying by 2 outside of it. And so that's the same answer. So I prefer the answers with whole numbers and not like fractions and fractions if possible. So if you can simplify yours, that'd be great, but it's technically not wrong.
Okay, so you don't like that one?
I'd prefer that it would be written like this because it's just, you technically have a fraction and a fraction. Does that make sense? And that's kind of like bad math grammar.
Okay.
But if you can change yours into being this one is totally fine. So in general, probably it's easier to not use fractions and try to use whole numbers. But you're not wrong. Okay. Is everyone all right with that? There's a couple of those in your practice thing, so look at your notes, try to do them. It's gonna be on your test, I absolutely promise.
So is that the answer? Just like-
Yeah, the answer is this. So like it turns out this thing simplifies to that. And notice how we had trig functions, they simplified us stuff without any trig functions at all. It's a little bit weird, isn't it? Kind of freaked me out the first time. I was like, what happened? Does anybody have a fancy calculator like a TI-89 or an Inspire? I think it will even tell you that this happens to it. Like if you type in, I'm not positive, but because I haven't checked recently, if you type in sine tan inverse of 2x, it might even simplify it. It's possible. We can give it a shot and see if it works, but yeah. Okay, the one inverse trig function I care you know the graph of is tan inverse. That's the sort of most important one. The ones of inverse cosine and inverse sine are not quite as important. So where does regular tangent have asymptotes?
Pi over 2 and negative pi.
Pi over 2 and negative pi over 2. Okay, so this is the restricted portion of regular tangent. Okay, so there's y equals tangent of x. And technically, it has vertical asymptotes at x equals plus or minus pi over 2. Yes? Okay. So when you find the inverse, you flip-flop x and y. Everything that was x becomes y and vice versa, right? So for y equals tan inverse of x, those are instead of x equals, what are they going to be? I'll move it up so you can, they'll be y equals. And if they're y equals lines, are they horizontal or vertical? Horizontal. So let's just call this pi halves. I'm now going to have a horizontal asymptote at pi halves and at negative pi halves. And do you remember how inverses were reflections across this diagonal line that goes through the origin down the middle? Does that ring a bell? So what's going to happen then is this part that's right here is going to reflect and now go like this. And this part that's down here is going to look like this. And from that picture, you can like answer some questions. We're not going to get to this really in this class explicitly, but this, you'll see this in calculus. The limit as x goes to infinity of tan inverse of x. What that means is as the x's get bigger and bigger and bigger, what happens to the y values of that picture? So as the x's get bigger and bigger, where do the y values go? Pi over 2. And if I said limit as x goes to negative infinity, that means as the x's get more and more and more negative, so like along this part of the picture, where do the y values go? Negative pi over 2. And one thing you'll do in calculus is find these limits for all sorts of functions, but it can often involve looking at a picture and looking at what happens to the y's as the x's get large. Okay. And then the other sort of really, really big focus of the test will be simplifying stuff and solving trigonometric equations. There will not be a whole lot that involves identities you don't have to memorize because I don't think they're quite as important, but you'll have that same list that you had on your quiz on Monday. All right, so, and the general strategy for dealing with identities is to try to start with the more complicated side and make it into the easy side, right? So what's the more complicated side here?
Left.
The left, yeah. So we'll start with 1 minus sine x minus cosine x, the whole thing squared, over cosine x. And there's no like immediate obvious canceling that can happen, so what's your first instinct as to what you could try?
Distribute.
So square out that sine x minus cosine x. 1 minus, I'm gonna write it just, I'm gonna do it a little bit longer. You don't have to take this much, write this much work if you can do this in your head. And I'm going to make a mistake on purpose. So that's sine squared x minus how many sines, cosines? 2. And then plus cosine squared x, and what did I forget? Parentheses. Over cosine x. If you can square that in your head and you know it's sine squared minus 2 sine x cosine x plus cosine squared, do it, because it's good to be fast at that. All right, from there, what simplifies? What do you see that actually adds up to some specific nice number?
1 minus sine squared x plus cosine squared.
Mm-hmm. Oh, I was thinking even easier. How about this? 1 minus, if I rearrange this into sine squared x plus cosine squared x,
Oh, you can reduce that to 1.
I don't even have to do that really, but what does the sine squared plus cosine squared actually add up to? 1. That's the first thing you should look for, is do I have anything that adds up to 1? That's the easiest thing. So 1 minus 1 minus 2. Okay. And then when you distribute that negative, what happens to the ones? They cancel. What happens to the negative sign? It also goes away. So you've got 2 sine x cosine x over cosine x. And then do a happy dance. Why are you doing a happy dance?
Because now it's almost done.
Because now it's almost done. You get 2 sine x, and you make your like big old box saying, yeah, I proved it. Woo!
We distribute the negative first.
You distribute the negative first. Does that make sense what happened there? I just kind of skipped that because I got lazy.
Oh, okay, I was gonna say, so we could distribute it on.
You could distribute it here, but I wouldn't suggest doing that until you've recognized that sine squared plus cosine squared is 1. Right, does that make sense? I would simplify the stuff that you've distributed as much as you possibly can before you distribute. And something to watch for is that do I have a sine squared and a cosine squared? It's kind of the really basic one you have to know really, really well to be able to spot it. Okay, this one might take a little bit more space, so write a little bit small, just warning. So which side obviously is the more complicated side? The left side. So we're going to start with the secant x, oh my gosh, minus cosine x over 1 plus sine x. And if all else fails, change your secants and cosecants and tangents into cosines and sines, right? So secant is 1 over. Okay. So I'm going to erase that a little bit big, leave myself some space, because if I have 2 fractions and I need to somehow simplify them, what do we think the best strategy is? Common denominator, exactly. So what does the first ratio get multiplied by? 1 plus sine x over 1 plus sine x. And the second one by Gesundheit. Over cosine x. So that makes 1 plus sine x over cosine x times 1 plus sine x minus cosine squared x over cosine x times 1 plus sine x. Or 1 plus sine x minus cosine squared x over cosine x times 1 plus sine x. Okay. Is everyone with me to that step? Yes? Okay. And there's nothing you can do right now because you've got cosine squareds and sine squareds in the numerator, right? Well, you know that sine squared x plus cosine squared x equals 1, right? That's the, you really have to know that. Can you change those cosines into sines? You see what I'm saying? You can say cosine squared x is actually equal to 1 minus sine squared x, right? That's a common strategy. If you see a cosine squared and you have other things that involve sines, make the cosine squared into sine squared. Okay, so I'm going to plug in 1 minus sine squared x for this cosine squared x. And because I'm plugging in something that has two terms, you have to use parentheses. So 1 plus sine x minus parenthesis 1 minus sine squared x all over cosine x 1 plus sine x. And we're actually really almost done now. It's not so bad. Once that negative distributes, what's going to cancel? The ones and also the negative sign, right? So we're going to have sine x plus sine squared x over cosine x times 1 plus sine x. And I say 2 more steps, okay? Is there any way you can simplify the numerator just a tad? Take out a sine x, great. Oh, yeah. Why are you doing your happy dance? Not just because the semester's almost over. Yes, Natalie?
I did it a little differently, towards the top when it said 1 plus sine x minus cosine squared x.
Mm-hmm.
I changed 1 minus cosine squared x into sine squared x.
Oh, that also works. Yep, that's a good strategy as well. Yep, yep. You just ended up with less steps than us. Totally fine, but you ended up kind of with sine x plus sine squared x, right? Yep, okay, no, that's totally fine. So this will equal sine x over cosine x because the 1 plus sine x and they cancel, right? And that's the same thing as tangent, right? Is that what you had to show? Okay. So Natalie's strategy, which is totally a good one, she noticed that she actually had a 1 minus cosine squared x, and what she did was made this into sine x plus sine squared x right away. Do you see that? That was good. Good job. You're welcome. Okay, I wouldn't have seen that. I didn't see that, but I mean, it works just fine. Okay. And the other sort of large thing you'll have to know how to do is solve equations, because this is something that's pretty important as well. So really your test will focus much more heavily on section 7.1 and section 7.5. Does that make sense? Plus chapter 6 is pretty much all there, but of 7, it's 7.1 and 7.5, they're the most important. Okay, so if you want, and this says all real x, you've got to find an expression probably going to involve some n's and stuff. So get the cosine x by itself first, right? So root 2 cosine x equals minus 1. Cosine x equals negative 1 over root 2, right? So cosine x equals negative root 2 over 2. Is everyone okay with that? Yes. All right, so in which quadrants is the cosine function negative? 2 and 3. Great, this quadrant and this quadrant. So that's the 45 or pi quarters degree angle. So what is that first pi quarter degree angle where the cosine is negative root 2 over 2? 3 pi over 4. And how about the other one? 5 pi over 4. And if I'd said stay between 0 and 2 pi, those would be your answers, right? But because I said you have to go for all real x, what do you have to add on to both of them?
2 pi n.
2 pi n, where n stands for an integer, but that means you can go 3 pi quarters plus around the unit circle once or twice or 4, 3, 7, 12, or negative times as well, going backwards. So that if you need all real x, you're going to have that plus 2 pi n. And I'll give you most of the credit for knowing 3 pi quarters and 5 pi quarters and just like spacing out the rest of it, but I will be checking to see if you know that. Okay. This one will be the same thing as tan x equals 1, right? which means the sine and cosine must be the same, as in equal to each other, right? At what angles does that occur? Pi over 4 and 5 pi over 4. And those points are spaced equally around the unit circles. You can actually write them as 1. You can say pi over 4 plus pi n. Okay, so I'm going to actually want you to write them in the most compressed form possible. So if you wrote pi over 4 plus 2 pi n, and you wrote 5 pi over 4 plus 2 pi n, I'm going to give you almost all of the points, okay? But I want you to recognize, when can I condense it down to one list versus when do I have to have two? And that's based upon whether or not these, you can add a number to get from this one to this one to that one, and it's the same number every time. Does that make sense? Okay. All right, and then the last kind you're gonna have to know how to figure out are the ones that involve some kind of factoring. Just because of time, I did a more complicated one in class. There's a couple easier ones on your notes on your review you've also got to know how to do. So a couple things make this one more complicated. The first thing is that you've got sine squared, and this is a cosine, right? So the first thing you gotta do is change those signs into cosines. So sine squared x plus cosine squared x equals 1. I just wrote something you couldn't see, didn't I? Sorry. So therefore, sine squared x is 1 minus cosine squared x, right? So that's the first step. Make them all the same kind of trig function. So you got 2 times 1 minus cosine squared x minus 3 cosine x equals 0. Or 2 minus 2 cosine squared x minus 3 cosine x equals 0. And I'm going to rearrange them so the biggest powers are first. Negative 2 cosine squared x minus 3 cosine x plus 2. And I'll pause and let you catch up. If something doesn't make sense, please tell me. Yes. Where did, oh, the negative in front of the cosine squared? Okay, good. If you're factoring in general, do you want the first term to be negative?
No.
Not usually. So take this and either multiply or divide by -1. Basically flip-flop all the signs, right? So that becomes 2 cosine squared x plus 3 cosine of x minus 2. And then we're going to factor from there. And most of these will be pretty easy factoring to be able to guess and check, even if it's not your favorite way to do it. We have to have one term that has 2 cosine x and one term that has singular cosine x. And you need a negative in one of them, and it's not quite clear which one, right? Yeah. So then you'll have to, so this is because this times this makes 2 cosine squared. And these, one has to be negative and one has to be positive because they multiply to make a negative. What do these numbers that go in those blank spaces have to multiply to make? -2. So would doing, just a guess, would doing this
No.
work? Okay, everyone said no quickly, but let's flip-flop them. Let's make that, so we want to make the first one. -1, okay. Second one you want to make +2. Let's check. So that makes 4 cosine x minus 1. Good job. Okay, so now you solve each equation individually. 2 cosine x minus 1 equals 0. 2 cosine x equals 1. Cosine x is a half. The other one is cosine x plus 2 equals 0. Cosine x equals -2. Why is that one super easy? Yep, it's not in the right. Cosine never equals -2. You don't have, does that make sense? So there's no solution from that equation. So you're just solving cosine x equals a half. And so in your unit circle, what quadrants is that? 1 and 4, spectacular. And is it pi 6 or is it pi thirds? Pi thirds, so x equals pi thirds is 1. And the other one is either negative pi thirds or 5 pi thirds, right? And is that good enough, or do you need plus some stuff? Plus 2 pi n. And are those two answers candidates that could have been combined? No.
What if you said plus or minus pi over 3?
I think that's probably okay. So I think that, yeah, you could say plus or minus pi over 3 plus 2 pi n. Yep, I think that's all right.
It's unnecessary because n could be a negative integer.
No, because that would, I think it's better, Cole, probably to list them separately, so please just do that, but I'm not 100% certain how kosher that is, but yeah.
Oh, I see.
You see what he's saying? Because he's saying he could just say plus or minus pi over 3, and then have one that was positive pi over 3 plus 2 pi and was negative pi over 3 plus 2 pi n. Okay, so everybody make sure you get a review packet. That's due tomorrow. Same one you got yesterday. So if you just didn't get one yesterday, grab one. I'll post solutions to that and all the quizzes